Hi everyone. In the last video, we have shown you how to design a dual mode resonator using a 180 degrees transmission lines, and with a small tricks by placing an inductor shunted at the midpoint to the ground is able to construct the dual mode resonance using a single transmission line, and this would reduce the size by half. And today's video, I'm going to show you how to extend the design by constructing an higher order filters by cascading the dual mode resonators. So let's drag in the ports for the input and the output, and we need the source to couple to the resonator through a capacitor, and we can plug in the transmission lines, 50 ohms lines, and the frequencies we set it to be 1 gigahertz, and the electrical length is 90 degrees as shown in the last video. And here we place an inductor at the center so that a dual mode resonators can be formed. So we make all the connections, and these capacitors set it to be 0.5 picofarad as shown in the last video. Oh, so we missed one capacitor here. Okay, so we haven't defined the inductance value. Let's put it as 0.2 nanohenry. So before we click the simulation button, we shall go to the setting page to define our frequency range of the simulation. Let's make it 0.5 gigahertz to 1.5 gigahertz, and the number of points can be set by the default values, which is 201 points. So here we go. We have a dual mode resonance response formed as a filter. However, in most cases, the rejections may not sufficient for certain applications. As an example here, let's say we want to increase the stop band rejections from 30 dB to perhaps 50 dB. So in this case, we will have to increase the number of resonators. So the beauty of this dual mode resonator is that we can easily cascade another section. So let's copy the entire circuit. Control C and Control V for the copy and paste action. Okay, so we can delete one capacitor here since they are connected in series, so it can be treated as one. And given for the same values without changing the parameters of the capacitors, inductors, and the transmission lines, the response deteriorates. So what we're going to do now is I'm going to show you how we can use the EDS to tune the parameters easily. So we just have to go to this Explorer here. So here we can add the variables for tuning. As an example, we add C1 for the capacitor, and we enable the tuning for C1, and we have C2 as well, and we also have the inductor L, let's say L1, 0.2, and we may want to tune the transmission line as well, TL1. By default, it was 90 degrees. So all these parameters tuning are enabled. So you can come to the bottom tab here. There is a tuning button. So here automatically you would update all the parameters that are being enabled by the users with the default values. And we can always change the range for tuning. Let's say 1.5 for C1, 1.5, 1.3 for C2, and 1 for L1, and this 150 for TL1. So you automatically define the range, and you can also change the step size for each tuning. So I will prescribe the nominal values of C1. Oh yeah, before I do the tuning, I have to define the parameter in my schematic. So this is correspond to C1, and this is C2, and this is C1. Since we're going to make it as a symmetrical design, and this will be L1, similar to this inductor. And we enable this transmission line to be tuned as well to give a certain degree of freedom. So this one, the parameter was defined as TL1. Okay, so now we are ready for the tuning. Let's say I change my, I can show you. Okay, let's enlarge the graphs. So for each tuning of the parameters, the response will change automatically, like instance. As you can see, it's responding on the graphs. So you can make use of the tuning features to perform the simulation and closer to your desired response. Okay, so I have a set of prescribed values for C1, which is 0.84, and for the C2, 0.14, and for the L1, 0.46. So these are the pre-calculated values, and the TL1 is 11.7. Oh, C2, because the minimum values is 0.25, so we cannot go below 0.25 unless we change it to 0.1, then our nominal values can be changed to 0.14. So here you can see a pretty nice response, the filtering response, fourth order. As you can see, there are 4 poles here. There are 4 resonants. We simply, with a cascade of 2 dual mode resonators. And if you look at the rejections here, is giving 60 dB of rejections. We can enlarge the center passband by changing the frequency range from 0.5 to 0.8 gigahertz. Sorry, I missed the G here. Okay. Oops. So let's make it 1 gigahertz. All right, so the center frequency is around 0.85, so we shall make it symmetrical. Let's say 0.7 gigahertz to 1.05 gigahertz. Yeah, so It's pretty nice response with 4 poles at the pass band. Of course, you can still fine-tune the response if you want to get a better return loss for your design. As you can see, the graph is changing as you tune the parameters. Yeah, so as a summary, this video has shown you how to design a high-order filters with the use of the dual mode resonators. And also, you can make use of the tuning features in EDS to tune the parameters so that to achieve the response closer to the desired one easily. Thank you.